Hi, everyone, and welcome to a new edition of the virtual seminar on geometry with symmetries. Today, it's my great pleasure to welcome Patric Donovan from the University of New South Wales here in Australia. And he'll be talking about bubble sheets and kappa solutions in four-dimensional Ricci flow. So take it away, Patrick.
Thank you, Ramiro. Sorry for the long title this morning. Yeah, so today I'm going to be talking about bubble sheets, kappa solutions. So kappa solutions is obviously a very big topic in Ricci flow. So this might be, a bit more seminal and a bit less new research focused, but we might still see some new results at the end. In particular, really, as we work to four-dimensional Ricci flow, seeing that, if I truly want to be able to kind of do everything, we might ever have aspirations of doing in four-dimensional Ricci flow, I really need to deal with the bubble sheet. And having a quick look at what's going on there. Okay, so Ricci flow, hopefully everyone here has heard about it. So I'm going to actually use the notation for Ricci flow being actually a solution to Ricci flow, the PDE here, obviously. What is the importance of this? Well, of course, this has been used, as the primary technique in many, many proofs recently. Most famously, I'll say, of course, the Poincare conjecture, or maybe slightly more importantly for us, Thurston's geometrization. But regardless, really, what's the point here? I've got, some parabolic or weakly parabolic PDE. It's going to do nice things to my metric, generically overall, hopefully. But maybe there are some problems with this, and as long as I can keep doing this flow, things should be getting better, and maybe that can give me some kind of uniformization. But we need to fix the problems that are going to happen. Okay, so let's just see what the problems are. Okay, let's start with Hamilton's original theorem of long-time existence and uniqueness. So for any compact smooth initial conditions, I have a maximal Ricci flow, and if it doesn't go, if it's not immortal, it doesn't exist for all time after the initial condition, then I need some curvature blow up. So curvature needs to blow up if I'm going to have to stop Ricci flow somewhere. Okay, as I've so graciously illustrated here. Okay, one obvious way to kind of try and get around curvature blowing up is to say, well, if I just rescale so that, my maximum curvature is 1, say, or, something like this, I'm probably not going to have a curvature blow up, but I might have some other problems. But if I do this in, dimension 2, of course, I'm already done. So in dimension 2, the way I get around this problem is just to say, I'm going to renormalize, and we're just going to set volume to be constant. Okay, one way to do this is to instead look at Ricci flows to look at a slightly different equation, where I'm going to add this extra term here. Oh, sorry about that. I'm going to add an extra term, and by doing this, now I'm getting a rescaled solution to Ricci flow. I might reparameterize as well, of course, and now this new solution has constant volume. Okay, if I have constant volume and I'm hopefully not doing anything too bad, then ideally I'm going to exist for all time, and indeed that's what we see Hamilton shows. Okay, and then based on this long time existence, now I can actually get some very nice geometrical results, and I get rewarded for my work. Okay, in particular, if I'm compact oriented, just to deal with the case where if I have 0 holes, and then I only need to deal with S2, then we see that as this flow continues, I go to a metric with constant curvature. Okay, so very nice and rewarding. At least this slide makes it not look too difficult, but slightly more difficult. But really, the problem is this starts to break down in 3 dimensions, of course. So what goes wrong? So I'm going to thank Angen, Eisenberg, and Knopf for their work on rotationally invariant Ricci flow and non-degenerate neck pinches here, and degenerate neck pinches as well. But there is, of course, a lot of people that have worked on things like this. To see that, okay, if I do Ricci flow in dimension 3, things genuinely do go wrong. So let's start with something very simple. I start with S3, and it's rotationally invariant. And I have, say, 3 S2s in here of radius R1, R2, and R3. and see what, can happen to Ricci flow as I change R1, R2, and R3. Okay, if I make them loosely the same, I get this case on the left here, where, we see exactly what we saw in dimension 2. Okay, I can keep doing the flow for as long as I want until I get a singularity, but, I can rescale whatever. Through the limit, I'm going to see that I'm just a round sphere. I get exactly what I want. Okay, some nice geometrical consequences of, starting with, Ricci curvature, or scalar curvature, non-negative curvature, whatever you want to say. But if I, start a little bit more complicated, so for example, on the right here, where my middle radius is sufficient, like a lot smaller than the other two, what I'm going to see is the intrinsic curvature of my middle sphere is going to cause it to shrink so that I get a neck occurring, okay? So this is going to vanish before the rest of the manifold does under Ricci flow, which means I do have a genuine problem, okay? I can't rescale this away. So I don't know how I'm going to deal with that yet, but let's actually look a little bit further. If I kind of, if I were to fix the left radius and the middle radius smaller and then move the right one, if I'm very small, I'm going to, get extinction in this left case. As I'm very big, I'm going to get a neck. So maybe there's some critical value in the middle, and indeed there is. So that's this middle case. So if I choose the exact right values for R1, R2, and R3, as I evolve through, what I'm getting is this tip is going to be formed. So, I just get one point where my curvature is blowing up. And now I can't, of course, go through Ricci flow. My curvature is blowing up. So I get, at least 3 different cases here that I need to contend with. Okay, of course, on the left, I don't really need to contend with it, but I get 2 more things that I need to deal with. So we really need to understand what's going on here if we want to flow past these times. Okay, so I said rescale in dimension 2. Let's try and do the same thing. Okay, so pick points where hopefully my curvature is going to be very big, or pick points near where I'm going to get problematic and times as well. I'm just going to rescale according to what the curvature is here. What this is going to do is going to mean, okay, now my curvature is going to go, not shooting off to infinity. And in particular, not only can I do this just to the metric, but I can get an entire flow, because the Ricci flow is invariant under parabolic rescaling. By rescaling the entire flow according to curvature, well, I'm now going to get another flow, and at this final time just being time 0, not being when it actually extinguishes itself, I'm going to see my curvatures getting better and better, and in particular, I'm focusing more and more on this area that I have a problem of. Okay, of course, I need to actually pass through the limit here. So what's going to allow me to do that? Well, Hamilton does this. This is still quite old results. But Hamilton's compactness theorem is really what helps us here. So if I have a sequence of completed pointed Ricci flows that exist at least till time 0, and Ti is bounded below negative, some negative number, and my curvature is uniformly bounded, and I have some injectivity radius thing at time 0. So as long as that's bounded above 0, then after passing through a subsequence, I indeed get convergence. In the C infinity sense, Chekhov-Gromov, Hamilton, C infinity, compact subsets, convergence on compact subsets on compact time slices. Okay, I get a final, Ricci flow. So here I can see, yeah, okay, sweet. After passing through some subsequence, I'm going to get a Ricci flow limit here. So to understand what happens in these singularities, hopefully I should just need to understand what happens in these ancient Ricci flows. But of course, there's a big problem here. My requiring some injectivity radius thing, is not really, doesn't seem obvious why I, will satisfy that or need it. And that's one of Perelman's really big contributions, is to introduce a kappa non-collapsing thing. Okay, so let's define it. So I'm going to say my Riemannian manifold is kappa non-collapsed at some scale. If whenever I'm smaller than this scale, my curvature, my volume is just controlled by my curvature up to some kappa here. And particularly, the really important thing is if I have a compact Ricci flow, then I'm going to be kappa non-collapsed at scales less than 1, we'll say, it's less than any fixed number, for any sufficiently small kappa. Okay, and kappa only depends on your initial metric and your time here. Okay, so what that means is that, well, once I fix my initial metric and I go through these things, well, all I really needed my injectivity radius for was for a volume bound. And now I have a volume bound. And in particular, when I'm rescaling, my volume bound is getting better. So in particular, not only do I get rid of the injectivity radius estimate I need in Hamilton's compactness theorem, but I'm also going to see that my singularity models are kappa non-collapsed at all scales. So finally, we can actually define what a singularity model is. So if I have some maximal compact Ricci flow, it exists up to time big T, and the curvature is blowing up at time big T, then I take a sequence of points and times such that its curvature is essentially maximal for all previous times and points, for spatial points and previous times. Then I just rescale according to this curvature. And sweet, now I can, using Perelman and Hamilton's compactness results, pass through a subsequence and I get convergence in this C infinity sense to a complete ancient solution. And I'm going to call this a singularity model. So we have quite a few properties of this singularity model now. Well, first of all, it's not going to be flat because at time 0, I do have genuine curvature because I've rescaled to have norm of curvature 1 at this point. Okay. Secondly, like I said, this kappa non-collapsing is something you can actually pass through the limit. So I'm going to get kappa non-collapsed at all scales. Thirdly, my solutions exist for more and more negative time because my curvature, the thing I'm getting rescaling by, is getting larger and larger. So this means that in the limit, I'm going to be ancient. Okay. Well, I'm an ancient Ricci flow. Of course, I have a lot of results I can apply to this. I've got maximum weak and strong maximum principle. In particular, Chen tells us that, if I'm a complete ancient Ricci flow, then I necessarily have non-negative scalar curvature. Moreover, by applying the strong maximum principle to this, what I'm going to see is that, well, if I'm connected as well, then I either am Ricci flat, in particular, I'm scalar flat, and that implies I'm going to be Ricci flat by looking at the scalar curvature equation, or I have positive scalar curvature. Okay. For us, what we're going to eventually do is to say I have positive or non-negative curvature operator. So really, I just need to insist that either I'm flat or I have positive scalar curvature. Okay. And then the last thing, which is actually very genuinely quite useful, is to say in dimension 3, because of Hamilton's pinching, what I will actually see is that, well, not only do I have non-negative scalar curvature, but I have non-negative curvature operator, non-negative sectional curvature here. Okay, this is actually very, very powerful and is going to motivate what I call a kappa solution. Okay, so let's give a definition. I'm going to say a kappa solution is a complete ancient Ricci flow. Ancient, and it's called a kappa solution if I'm kappa non-collapsed at all scales. I have non-negative curvature operator. I'm not flat. And my scalar curvature is uniformly bounded. Of course, having non-negative curvature operator means scalar curvature uniformly bounded bounds everything. Okay, well, the only thing I'm really adding here is that I have non-negative curvature operator. In dimension 2 and dimension 3, I really haven't added anything because in dimension 2, all I have is scalar curvature. And in dimension 3, because of the result we saw on the previous page, indeed, I do have this non-negative curvature operator. But in dimensions 4 and above, this is a lot of added information that is not necessarily true for singularity models. But in dimension 2 and 3, if I want to understand these guys, it's sufficient to look at kappa solutions. And in particular, that's going to play a big role in Hamilton's proof of these really big results, Poincare conjecture and Thurston's geometrization. So let's actually have a quick look at what's going on. Okay, so let's go back to this model we saw earlier of the rotationally invariant compact Ricci flows on S3. Well, on the left case, well, clearly I just rescale and I'm just going to get the sphere. And on the right case, I'm going to rescale and I get better and better necks. So in the end, I just become the standard cylinder. Okay, and in the middle, well, I get a sequence of points and times going to this tip. And if I rescale, I actually get something called the Bryant soliton, which looks a lot like Hamilton's cigar soliton, but it blows up like a paraboloid now in dimension 3. So this is going to be kappa non-collapsed. So in all of these cases, I get something new, and on the left, I can rescale, whatever, we saw that. But on the middle and on the right, now I see that, well, if I want to continue doing Ricci flow, one possible idea is to say, okay, understand what these regions are very well and get some kind of canonical neighborhood theorem and now remove them. So that's exactly what Perelman does. So, I would say the biggest part of Perelman's proof, maybe I don't have the authority to say this, but, at least I would say is understanding what these regions are. Okay, this is, really the majority of his argument is to say, if I have some kappa solution, what does it look like? Okay, he does conjecture about what it is, isn't quite able to prove what they are, but is able to get very, very good control on them. In particular, his kappa non-collapsing says, I'm not going to get a cigar times a line, and this was something Hamilton was having difficulty removing this case. Regardless, being able to have really good control on these guys, like I was saying, is being able to say that I start with any initial condition, I'm going to flow, maybe I'm going to get a problem, but if I know I have a problem, it comes from a singularity model, and therefore a kappa solution. I know what kappa solutions generically look like, so I can model this region, and then I know what to cut out and do surgery, and then I can continue doing, and this allows me to continue doing Ricci flow, and now I get rewarded by getting, these big results Perelman proved. Okay, so if I want to even have a chance of doing this in dimension 4, let's start with kappa solutions, okay? Let's start with the ones where I have this very strong curvature condition. In Ricci flow, this is essentially the second strongest curvature condition that I know is preserved under Ricci flow. There's many, many weaker ones, and there's very, very few stronger ones. So let's actually see what has been done in dimension 2 and 3, and in particular how. In dimension 2, I mean, we've already seen this. The only genuine singularity model I can get is the round metric. So the round shrinking spheres. Okay, but it's actually possible to classify ancient Ricci flows just with bounded curvature. I don't need kappa non-collapsedness in dimension 2 to find this classification. So this is done by Daskalopoulos, Šešum, Chu, and Hamilton as well. And we see that not only do I get the round metric and the flat Euclidean space, but I get the cigar and a killing Rosenau solution, which is going to be similar to a Perelman oval we see on the next page, but with cigars. So in particular, it looks like two cigars glued together, and it has the distance between the tips increases as I go backwards in time. Okay, so I can see what I am in dimension 2, and in particular, all of these guys are going to generalize to dimension 3, where, of course, instead of considering kind of this flat guy, what I'm going to do is take a quotient and have the neck. Okay, so in dimension 3, I can actually do this now because of the work done in Brendle and friends. Okay, so what actually are these guys? Well, first of all, I have my round metric. Now I have my neck. And then now I also have the Bryant soliton and the Perelman oval, where the Perelman oval is done by gluing together two Bryant solitons on the tips, and then a cylinder in the middle, and then mollifying and taking a limit and things like this. Okay, well, as in dimension 2, something to note is, well, if I look at the isometry groups here, they're all pretty large. Like I have a lot of symmetries here, and hopefully that can help me do this classification. So at least, well, in dimension 2, we saw, okay, I have O2 invariant at least everywhere. So I'm rotationally symmetric. You can actually prove this a priori in, say, the compact case. Here, what I can see is I'm O3 invariant. Do you have a question, Ramiro?
Yes, just a quick reminder for myself. So the oval, except for the tips, it's fibered over an interval. The fibers are round spheres, right? Two spheres,
Yes.
round two
So,
sphere.
yeah. So,
Okay,
I mean, in particular, the fact it's
of
O3
different
invariant
radii, of course.
mean, yeah. So everything here is actually fibered by round spheres. It
So they are
depends.
rotationally symmetric.
Yeah, yeah. So
Alright.
all of these, the fact that I have O3 inside all of these means that I'm going to be rotationally symmetric. So the Bryant soliton, I have this round ones like this. And what I'm going to do is, have one here and one on this end. and then I'm going to connect them with a cylinder. And then you mollify. But of course, the round spheres that I'm fibering by are going to increase in radii, because otherwise that'd be kappa collapse rather. Yeah. So that's what the Perelman oval is here. Okay, so the question is, like I was saying, okay, sweet, I'm rotationally invariant. Maybe let's use that to help us in our classification here. So maybe step one, if I'm rotationally invariant, what am I? Can I prove I'm these four guys? And step two, if I'm a kappa non-collapsed ancient Ricci flow, bounded curvature and all this, non-negative curvature operator, can I show that I'm actually O3 invariant? So this first case might seem easier in comparison, and maybe it is, but it's still quite difficult. But the more astonishing here is, of course, the latter. Being able to, a priori say, I just have some curvature things, and now, I actually have, quite a large isometry group. I'm rotationally invariant. So let's actually see how to do this. So in this really first four cases, we can kind of do this. All I really care too much about is in the non-compact case. And then we can do this in the compact case by doing something similar. So there's quite a few steps to this. So first, I need to classify kappa non-collapsed gradient steady Ricci solitons. Also, shrinking gradient shrinking Ricci solitons will be helpful here. This is done. The reason is, as I pass through limits, I might have these guys, and having these guys means I can model solutions. So next I need to classify rotationally invariant ones. Actually, before I move on, something I might want to say, in this case, you can actually prove it using symmetry improvement as well. So techniques we're going to see later allow you to prove this, but initially it wasn't proven like that. Second thing is the Brine soliton is the only rotationally invariant one with positive curvature operator. Okay, if I don't have positive curvature operator, then I'm going to split a line and have something like a cylinder or a quotient thereof. So doing this second case now allows me to, finish my result essentially, as long as I get rotational invariance. So how do we do this? Well, this is the part I'm going to focus on, which is to say, I have some symmetry improvement result, and that's going to allow me to say, all my kappa solutions are actually rotationally invariant. So let's focus on this and say, how can we do this? Of course, after we've done that, we can then move to the compact case and say, the Perelman oval round shrinking sphere are the only compact ones. Yeah. So the previous slide, of course, I just did the simply connected ones. You can do quotients, so quotients of S3 and so forth. Okay. So these two steps, let's focus on them, see what's happening here. So symmetry improvement, what do I mean by this? So this is the key ingredient. So if I have some kappa solution, really what I want to be able to say is that if I have maybe even just an ancient Ricci flow or just a Ricci flow, exists on some region, and on some region is nearby a standard very symmetric solution, what I might hope, considering that Ricci flow preserves the isometry group, is that this symmetry at least will improve. Of course, I can't, genuinely gain an isometry group, but I can at least, in some meaningful sense get closer, so that, as I pass through the limit of, epsilon going to 0, whatever that means in epsilon symmetric, that I actually get something symmetric. Okay, so this is, a very loose terminology here, and I'm not going to actually define what it means to be epsilon symmetric here. I'm going to give a similar definition, but the definition done by Brendle is, of course, very, very complicated and deals with almost, killing fields, and CMC next, it's quite complicated and quite hairy. We're not going to get into the definition here. Okay, so first of all, I'm going to say what it means to be a neck, an epsilon neck. This is something that's at least not too difficult. Of course, the point is, as I'm going backwards in time, I'm going to become, maybe more and more neck-like, but this is, only going to be up to, how long I'm neck-like, the so amount of time I'm neck-like, the length in which I'm neck-like, and how close it is, and up to what order. So I'm going to parameterize all these things in epsilon because they're all going to get smaller. But in particular, I'm going to say, something is a neck if there's just a region which is neck-like. And I'm going to call this neck region U. So I'm going to call a Ricci flow neck-like if there's a region U, so that it is neck-like in the sense that it's a Ricci flow that exists for long negative time. It's a long actual interval on which it's neck-like. So the diameter of its fibers kind of is quite large. And then it's neck-like up to high order and is very close. Okay, so the good thing is now if I'm very close to a neck, I can actually say what it means to be symmetric. Okay, in particular, if I'm an epsilon neck and I have a neck region U, this is complete overkill, but this is fine. Then there exists an open set which is uniquely foliated by constant mean curvature spheres. So I've kind of illustrated this at the bottom. But the important thing here is this tells me what the orbits of an action should be. So in particular, if I am genuinely rotationally invariant, the CMC leaves are going to be the orbits of the action. So if I have an action of something nearby, then it should also be foliated by the CMC leaves. So this at least gives us enough information that hopefully I can say, well, if I'm nearby, then I have an action. If I have an action maybe up to an isometry of the spheres, then I average this and now I can say what it means to be symmetric. So let's do exactly that. So in this neck case, I can do this because of Hamilton's normal necks. So what is this? If I'm sufficiently close to the standard cylinder, I'm an epsilon neck, whatever, then up to a rotation of this S2, I can actually say that, necessarily what it looks like in the sense that I can give it a canonical parameterization. So a map from S2 times an interval into my space such that this is canonical in the sense that it's a harmonic map on standard spheres and unit speed parameterized, all this kind of stuff. And even better, that when I map the parameterization of just a vertical sphere, I get a CMC sphere. So that means that, well, this gives us a very good candidate for what an action would be, because I have a standard action on this guy on the left on my cylinder. So I can just move that action over to the right via this pullback, and sweet, now I have a canonical action up to some rotation, but if I fix a rotation, this won't really matter when I average. So the corollary I care about here is to say, if I have the space of metrics on my cylinder, I'm epsilon close to the standard cylinder, and then let curly A denote the space of O3 actions with O2 isotropy. In particular, it's just rotations on spheres. Then there exists a smooth function that maps from my metric into my space of actions such that it acts isometry if and only if it's rotationally invariant. Okay, so that tells me if I have kind of this almost canonical or essentially canonical action, and it's canonical just up to a rotation, what a canonical action should be, or what the canonical average should be. So this will be this G bar that I write in the next definition, okay? So I can say that a metric on, sorry, this should have been S2. A metric on S2 times R is epsilon symmetric if, for the same thing, I have, this difference is smaller than epsilon where I average out my metric, okay? Do note that we haven't been so careful here to deal with an interval. We're just dealing with all of R. That's not too much of an issue here. It's just really motivating what we mean to be epsilon symmetric. And now I can see that, if I have this symmetry improvement result, it's actually genuinely quite powerful, and it will allow us to get symmetry of our Ricci flows. So how do we do this? Well, the problem is I still need a lot of work to do, okay? We're going to need to take through quite a lot of sequences. So this means we're going to need another compactness theorem. So this is given to us by Perelman. So if I have a three-dimensional kappa solution, pointed kappa solutions, any sequence of times, I can rescale and I'm fine. So I get a convergence to another pointed kappa solution, okay? Rescaling here is just going to be with respect to curvature, but I can rescale with respect to anything as long as my curvature is remaining constant. So I'm compact modulo rescaling. Okay, well, this is very, very useful because now we can pass through limits. And an important consequence is that, or an important generalization is in high dimensions, if instead of taking, bounded and having non-negative curvature operator, I just take the Harnack inequality, then I still get compactness, and I'll get compactness with non-negative curvature operator and Harnack inequality as well. The problem here being that, as I pass through limits, bounded curvature is a lot more difficult to deal with than having something like a Harnack inequality. And, Perelman's actually able to show that if you just have a Harnack inequality in dimension 3, then you actually have bounded curvature, which is very powerful. Okay, so let's, use this. So, what we started with was ancient Ricci, well, just Ricci flows, and I worked to ancient Ricci flows and singularity models. Hopefully we can classify them. Maybe that's a bit too difficult. So let's do a similar procedure. Okay, now I'm going to go backwards in time and get something more regular, even better, and hopefully we can classify them and then model our kappa solutions on them. Okay, so this is what I'm going to say is by an asymptotic shrinker. So if I have a kappa solution, well, now I can just rescale backwards in time. Okay, I'm actually going to do this necessarily with the time component so that I'm, have the right curvature blow up, in particular, so that I'm going to be a shrinker. And I can do this as long as I stay within bounded reduced distance. Note that, the bounded reduced distance doesn't necessarily mean I'm staying within bounded distance. So, for example, on the Brine soliton, if I stay near the tip here, I'm going to get flat R4, which isn't a non-flat gradient shrinking Ricci soliton, but as I go back through time, I can escape off to spatial infinity here and get a cylinder. So, you can see in the Brine soliton, the only shrinker here is the cylinder. Okay, so once I know what the shrinkers are, maybe that might help me with my classification, seeing what happens at very, very negative times. So in particular, Perelman also proves that in dimension 3, a kappa non-collapsed gradient shrinking Ricci soliton with bounded sectional curvature must actually be compact. Well, perfect. I'm essentially done here, because now if I don't have, I think this should be bounded positive sectional curvature, then I must be compact. Well, that tells me I either have, a zero sectional curvature, or I'm just a shrinking sphere. And in particular, that tells me I'm going to be a cylinder, the round sphere, or a quotient. So finally, I can say that, okay, I might not know what my kappa solutions are, but as I go backwards in time, I have to look like a round sphere or a standard cylinder, at least in a very large region. Okay, so that's very nice. Unfortunately, as we saw in the Brine soliton, this isn't quite enough. So I still need to rescale that tip region better as well. Perelman does this too. So if I take regions near the tip of the Brine soliton, instead what I'm going to get is something else. But if I remove that, then all the rest looks like a neck. And in particular, Brendle says that, well, this region I'm getting rid of necessarily looks like a steady gradient Ricci soliton. And the classification of steady non-collapsed gradient Ricci solitons with non-negative curvature operator tells me that, well, this actually needs to be the Brine soliton. So finally, after all this work, I can say that if I have positive curvature operator, well, I have a region which looks a lot like a Brine soliton, and the rest of my region looks a lot like a neck. And in particular, this Brine soliton region being compact means I have very, very good control over it. Whereas this neck region just means I'm a neck region in the limit. So it's not quite as strong. So I need control over this neck region. And finally, we can use this symmetry improvement result. So what do I do? I have a sequence of points and times going backwards off to spatial infinity, or just times rather, where on the right I have a cap, which is Brine soliton, and I know that's symmetric. It's not quite a Brine soliton, but it's going to be a lot more symmetric than this neck-like region should be, as long as I'm not symmetric. So really what I need to do is to say, okay, on this sequence of times, this at least has, very, very small amount of symmetry in the sense of epsilon. And as long as I can do that for any epsilon, I mean, show it's epsilon symmetric for any epsilon bigger than 0, it's going to be symmetric for us. So our symmetry improvement net result now is going to be very useful. So how do we actually use this? Well, what I'm going to do is I want to show it's epsilon symmetric at this time. Well, if I look further backwards in time, I know I have, a larger time where I have this thing happening again. Whatever I have my cap region over here, but this neck region, well, I know eventually it has to be an epsilon neck, very, very close to an epsilon neck. In particular, for very, very large negative time, I'm going to be epsilon symmetric for any epsilon. And then I can just apply my symmetry improvement result to improve the symmetry until I get to this time I care about and say that, well, indeed, it is epsilon symmetric, okay? Because my symmetry improvement is going to take this from, some epsilon at some very negative time to an epsilon 2 to some, power. So it's going to be very, very symmetric. And indeed, we see that, well, because both regions here have to be symmetric for any epsilon, I'm actually going to be O3 symmetric. So this is how I get rotational symmetry. So it's a bit complicated, but in the end, from essentially nothing, I mean, a lot of curvature assumptions, I get rotational symmetry. So we can see that this is a very powerful result. Let's actually try and generalize this in higher dimensions now. So the first and probably most important thing to say here is it's kind of already been done in higher dimensions, but only to the sense that if I just want to generalize this result and use the exact methods I did to get it, well, I can do it. And in particular, if I want to do that, what should I say? I should say that I have uniform pick and weakly pick 2. So this is done by Brendle and friends again, now Nav, Daskalopoulos, and Šešum. And this is, of course, more recent. But the probably important thing to note here is, I mean, I don't need to assume weakly pick 2. I just need to assume weakly pick, or uniform pick, rather. Note that the uniform is doing a lot of work here. If I'm weakly pick, I'm even weaker and quite a lot weaker than non-negative curvature operator. So in this case, I've actually done a lot of work apart from kind of this boundary case where I'm pick but not uniform. So if I'm weakly pick, I'm going to pick up a lot of new results. So rather than going quite to weakly pick, let's just go to non-negative curvature operator. I'm still going to see a lot of results. Okay. So why would I pick uniform pick and weakly pick 2? Why would I assume these things? Well, the reason I do this is to say that, well, okay, good news, I'm still going to get a Harnack inequality, so I get all these compactness results I still want. And the second thing, and maybe what I want to focus a bit more on for the remainder, is to say that the only non-compact asymptotic shrinker I can get is a neck. So this only symmetry improvement I need to do is on necks. I don't need to deal with, S2 times R2. And that's actually what I'm going to focus on now. So in dimension 4, let's just say I have non-negative curvature operator. What else have we found? Well, actually quite a lot of things. So of course we have, an extra Einstein solution here, 2 of them rather, the Fubini-Studi metric and, S2 times S2. But I also have quite a lot of other solutions. So first of all, I have, oval times line, or, adding lines to my previous solutions. So that's my, bubble sheet, which I'm going to call S2 times R2. And I get the Bryan soliton with a line and, the Perelman oval with a line. Okay, and also I get 3 new ovals now. So I get 2 new ovals, Tim's oval and Haslhofer's oval. And then I also get Yilai's steady solitons. Note that when I put an asterisk here, I actually get a 1-parameter family of solutions. So this isn't even a finite list anymore. It's quite large, at least in comparison to this set of just 4 things. But Haslhofer was the most recent to add to this list, and he actually conjectures that it's done. So we should hopefully maybe know what all these things are. And indeed, I look at this and I say, okay, for the non-compact guys, at least I'm O3 symmetric. And the Fubini-Studi metric is much more symmetric than this. I don't quite have an O3 in there, but I have a lot more overall. So really a symmetry type argument, looking at this and saying, hopefully I can get symmetry from these conditions and then classify within symmetry might be a good approach still. So let's start with a much more simple question to say, are at least the non-compact kappa solutions O3 invariant? And how do I do this? Well, let's look at the asymptotic shrinkers. So what do I need to deal with? So in dimension 4, if I have a non-compact, non-flat, shrinking gradient Ricci soliton, and I have non-negative curvature operator, well, all I have is the neck or the bubble sheet or a finite quotient. So that tells me the next thing I need to do is look at the bubble sheet. This is really the first thing I need to do, okay? And genuinely, we can see this appears quite a lot, okay? So Tim's, down here, Tim's O3, O2 invariant kappa solution, this only has bubble sheets, but if I have a round, non-round, non-compact kappa solution, then what I get is a non-compact asymptotic shrinker. This should be non-round in here. Sorry. So I only need to deal with the non-compact case as long as I'm not round. And so really, I either have the neck or the bubble sheet. And for a lot of these guys, in particular for the ovals, I definitely get bubble sheets. So if I want to get this symmetry improvement result, like I'm saying, we really need to work with bubble sheets. Okay, so what progress has actually been made? Well, first of all, we don't even have a compactness theorem yet. And so let's try and do that. If I want to pass through limits, I'd need a compactness result. So let's see what we can do. In this case, we have bounded curvature, so it's actually quite difficult to get a compactness theorem result. In particular, I can say, if I have a sequence of 4-dimensional pointed kappa solutions, obviously I'm going to do the same thing as before, where I'm going to do modulo rescaling. Then I have a subsequence, and I can converge. So I get compactness, except for one case, which is quite difficult to remove, which is to say I have epsilon bubble sheets of scale r for arbitrarily small r and epsilon. In particular, I have a sequence of bubble sheets which look a lot like bubble sheets on long regions, long times, and things like this. And also it's very, very small. So that gets me a curvature blow up. But how do you resolve this in, say, dimension 3? Well, you can resolve this just by explicitly saying a Riemannian manifold can't have arbitrarily necks of arbitrarily epsilon necks of arbitrarily small scale for epsilon arbitrarily small. But unfortunately, in the bubble sheet case, this is a lot more difficult to work out. And we haven't quite been able to get there yet, but at least we're a lot closer to a compactness result, and we can see that bubble sheets again appear quite often. Okay, well, not quite there, but let's actually look at getting the action here. So what can we do with our symmetries? So something very important done recently is Lagache and Lynch have been able to show that, okay, the CMC parameterization or CMC foliation doesn't actually generalize. If I don't have necks anymore, but have more general bubble sheets, so like S, K, R, N, then I can't get a CMC foliation. Instead, I need something more general, and I'm going to call this a QPMC foliation. So that's a quasi-parallel mean curvature foliation, which is a very nice result. And again, because this comes from mean curvature, I can see that because I have a unique quasi-parallel mean curvature foliation, it's necessarily going to be the orbits of an action if I'm rotationally invariant on the bubble sheet, so O3 invariant. So, using this as, what should be the orbits, we can get an inverse function theorem result to tell us, okay, now I again have, necessary actions. So now if I have the space of metrics, epsilon close to the bubble sheet, standard bubble sheet, I can actually map smoothly into the space of actions and get what we might call, a canonical action here. But in this case, when I overlap, in Hamilton's case, in the neck case, I necessarily get isometries, whereas here it's a lot more difficult. Like it'll be epsilon isometries, and there's a lot more work to do. And the question we're asking is, okay, can this at least provide a framework for a symmetry improvement result? Now I know what symmetry, being epsilon symmetric means in dimension 4. Can I get a symmetry improvement result? So you can do this in dimension 3, but the question is, can you actually genuinely get it in dimension 4? And hopefully, now that all you need to deal with is the neck and the bubble sheet, with a substantial amount of work to do, you should be able to hopefully show that you're O3 invariant in the case of non-compact. Yeah, so that's all I had to talk about today. Thank you.
Thanks, Patrick. An interesting talk. Are there any questions for the speaker? Comments? So you said in the uniform peak case, the classification is known, right?
Yeah.
So
So
what's an example of a four-dimensional solution, which is, say a four-dimensional Riemannian manifold, which is not uniformly peak, but has non-positive curvature operator? Do you know?
No. So positive. Okay, that would need to be a compact guy. So positive curvature operator.
Non-negative, right? The positive curvature operator is a sphere. But,
Yeah. So,
I mean,
yeah.
not
So positive curvature operator. So curvature operator is a lot stronger than pick. So pick 2. So like kind of there's a. So let's just deal with the case of.
but you said that it's known in the uniformly peak case, right?
Yeah. So we've got a lot of extra examples here.
I think the key difference here is that when we say uniformly pick, that means in time as well as space.
Okay.
Oh, okay.
All right.
Sorry.
That
Yeah,
makes sense.
I don't think yeah, okay.
Thanks.
Yeah, so of course, like the new examples that have been constructed, they've all got positive curvature operator on the sphere, but yet they fail the uniformly pick assumption, thus being missed by the previous classification, precisely because of what happens as time goes to minus infinity.
Right.
Yeah.
Any other questions? Maybe better questions than the one I asked. And so do you have any idea on what's the potential approach for proving the symmetry improvement now that you know what are the candidates for killing fields? I don't know. Is it something similar to what Brendle does with this
it is.
parabolic equation for killing fields?
So that's a very, very similar approach. So in dimension 3, you can do a very similar thing, but instead of talking about killing fields, what you'd like to talk about is like this anti-symmetric part. So the work we did was essentially to not have to talk about almost killing fields. So now you have a symmetric part and kind of an anti-symmetric part of your metric. And now I look at the evolution of the anti-symmetric part.
Right.
Yeah, my hope is at least that we'll be able to make this a bit more geometric by, instead of working at the level of killing fields, working at the level of the group action itself.
Yeah, and also something I should say, which I don't think I did. This is, of course, work with Tim Buttsworth and Anusha, Krishnan.
I see. Yeah, but if I remember correctly, Brendle also uses the fact that you have a three-dimensional group. Right? At some crucial point to improve the estimate, he takes some D brackets, and anyway, we can discuss later. But very interesting. All right. If there are no other questions, let's thank the speaker again.